So let's travel a little. Let's travel north, somewhere where Scotland's Orkney Islands are, and then a little to the east, a place where it's not north enough, but doesn't consider itself east either. It's called Estonia. And near the capital city, there's a curious place called Kia, and near there we find two outcrops. First, the trench is a wild place. It goes down into the moist cave where bats live. Spooky. And from there we can find Estonians' own brown gold, the oil shale, that covers about Estonians' 70% energy needs. We can see right in a second, maybe. Oh yeah, the lithological features that tell us the retreat of the seawater that turned sea into the dry land. We can see bentonite layers that give a start to a violent collision of continents. And on top of that, there's a ditch that stands tall next to the concrete World War I bunkers. Now chilling silence remembers us past chaos, and the upper part of the succession is boring. There's nothing there, just argillicious limestone. So yeah, the sampling site could be more appealing for sure. I was introduced to Petri outcrops in my master's thesis, where I conducted Conodont biostratigraphy on Sandbian age rocks in regional Kukruse and Haljala stages. And the succession is 13 meters total, with some pretty interesting lithological features like oil shale and sedimentary gaps and bentonites. So yeah, I am a child of stratigraphy, but I found some interesting things that I want to share with you today. And the master thesis brought more problems than answers. So if we wanted to finish the story, we needed to take new samples. And I wanted another animals with me to do the stratigraphy, because just looking at conodonts, I can't really compare it with anything else. So bear with me for some slides of stratigraphy. At least in Baltoscandia, when biostratigraphy is done separately, like graptolites in one work group and conodonts in other, and when we ask where is the boundary between Kukruse and Haljala, then every animal speaks different story. And when we go to Petri outcrop and see the conodont results, the details, we just have to look at some zonal species like Baltoniodes variabilis, followed by Baltoniodes alabatos, seeing that the Baltoniodes gerdae is missing. So if you look at the scheme again, the boundary should be in the Baltoniodes gerdae subzone. So it's in the gap. It's quite easy to mark the boundary. The same pattern is with chitinozoans. Some key species are present and others are missing. So again, if you want to put boundary somewhere, it's easily to put it where the missing species are. And lastly, I also got conodonts, ostracods, and ostracods just basically tell us where the link between macro and microfauna are. So at least in the north West Estonia, it's quite easy to put boundary somewhere. But when we move away from like northeast Estonia or West Estonia and see where, and we can find a boundary in the Baltoscandian region and do it in a group work, at least that's what I'm trying to do, then we see that the boundary is a little shifting. So the next time you have to do stratigraphy, you should ask, is the work done separately or together, because there might be some differences, at least in the outcome. In better outcrop, when we look at Conodon's identifiable species elements per sample, we see that Kukruse age was a really optimal life conditions, not just Conodons, but for other species too. And just before those sedimentary gaps, we can see the decline, and on the top of it, we can see the Gutenberg excursion, which is basically worldwide known as a sea level rise and fall. But for some reasons, Conodons started to act on it even earlier, not in the upper Carrack age, but in a lower one. It's quite strange, but Männik has done some work on it, so if you're interested, go have a look. Another thing that I stumbled upon was we're living in an information age, and for some reasons, if I want to understand or look up how Conodons look like, I have to dig really deep into articles everywhere. But today's information age, this shouldn't be like that. We should have databases that I can just type in what Trypanoistodus suberectus looks like, and it should give us all the elements, what are they look like, where I can find it in the articles, and so forth. So I'm doing my own little pictures like that, and hopefully someday someone will take the fame and blame and will do it. Previously you saw, well, the Paltoniodes gerdae was missing, and these are how they look like, those small conodont elements. And before was variabilis and other abatus. Well, the funny thing is that there are many samples that are not one or the other. And one sense it could be that there is always a transition between one species to another. So if you're trying to do a stratigraphy, then you can't really pinpoint the precise place or in the succession where the boundary goes. So in literature, some authors are putting it or them to variabilis and other from Malabatus. So at least in Conodons, where we can do like precision stratigraphy, there is transitional zones. So next time, maybe in your animals, there might also be the transitional part of it, not one or any other. Then I took like almost 1,500 pictures of my Conodont elements and put it all together just to figure out like the more complex way of looking things. And I thought like when I'm going to do it, then I can get more precise results. And every Conodont animal should have like 6 or 7 elements in its feeding apparatus. But Scalpelodus, at first I found like maybe 6 of them, and then I dig deeper and I found another 6 or 7. So the more data I have, the more complex the system gets. So if you only find like one element, you can tell the big story, but if you get like thousands of them, you can see that the results are so contradictory. Or I still regret taking these pictures, because right now I just can't put like, oh, this Scalpelodus looks like that. I have like so many different pictures and so many different elements. How can I pinpoint to it? The last things I want to point out that even though I'm doing Conodont research, I found out that there are quite many other animals that I can extract from my everyday work. And probably every one of us who's doing some part of research can definitely add something to the extra, to the mix, to get your results more precise, more better for the community and the whole. So as you can see, there are craptolites and architarchs and scalacodonts and chitinozoans and everything. So yeah, the life of stratigraphy basically ends here, and I just want to conclude that should stratigraphy be a result of a teamwork, because the more animals we put into the mix, the more complex the system gets, and the boundaries start to shift. So the next time you're doing a stratigraphy work, see if the results are in somewhat different when doing separately. Then there is a transitional phase between species, at least in conodonts. We can see them. I don't know if it's seeable in your animals, what you're searching for, but they are there. Then more species equals more complex ways of looking at. When you have little, you can tell a lot because you have to make up all what's missing. But if you have very many, then you just have to work with what you got. And lastly, one's residue could be, others one's cold. We did, for example, sulfur isotopes from conodont heavy fraction residue. And we even got primary seawater results. So, and yesterday we saw quite many talks about geochemistry that can be added to your work to strengthen the community and get more precise results. So I definitely recommend searching what you got and what you have. That's it. Thank you.